Hello and welcome to this next video on topic 6 on inference and estimation. Here in part 4 we're going to be looking at interval estimation for a population proportion. In the previous two videos we looked at interval estimation for population means in two conditions: when the standard deviation of the population was known and when it was not known. So here we're looking at a different kind of variable, the categorical variable. So when the variable that we're interested in studying is in fact categorical, then the parameter that we are trying to infer about is now the population proportion rather than the population mean. So we've seen before that the point estimator for the population proportion P is what we call the sample proportion, or P hat. So we're in that scenario again where we have a population here represented by this large circle, and we would like to know about the population proportion P, which we may not know. We have this sample here that we take from that population, and let's say it has a sample size of n equal 1,000, as it did in this marijuana legalization example, and 560 out of 1,000 people indicated they agreed with legalizing marijuana. So 0.56 is our sample proportion, P hat, and that is estimating the population proportion P, which we don't know for sure here. So that's what we're trying to infer about, is this number right here, P, from this information that we have over here. So what we'd like to do here then is develop a set of intervals that, with different levels of confidence, are going to capture that value of P. From the previous video, we know that the general form of any confidence interval is going to look like this. It's going to be our point estimate plus or minus our margin of error. So for proportions then, our confidence interval is going to look like P hat, which is our point estimator, plus or minus some margin of error. So what we have to do now is establish what this part is, this margin. So recall that the margin error has two parts to it. It's composed of our confidence multiplier, and it's composed of our standard deviation of the sampling distribution. Remember, for the population mean, the total confidence interval looked like this. We have the sample mean plus or minus the entire margin of error here. So here are the two pieces we're talking about. Here's our confidence multiplier, and that's multiplied by the standard deviation of the sampling distribution. For the situation where we're looking for the population proportion, we know that under certain conditions that P hat will have the sampling distribution for P hat will have a normal distribution with a mean of P and a standard deviation equal to this value here. That came from a previous topic. And so if n times P was greater than or equal to 10, and n times 1 minus P was also greater than or equal to 10, then we could assume that the sampling distribution of sample proportions was normally distributed. So if we put all of that together, we could then say that for a proportion, the confidence interval for P, the population proportion, should be the following. It's our point estimator P hat plus or minus our Z star value, our confidence multiplier, and then multiplied by the standard deviation of the sampling distribution. But there's a problem here. If you think about it, what we're trying to do here is estimate the unknown population proportion P. That's the whole point of this process. So having it appear up here in the expression for the standard deviation is a bit problematic. So we're going to overcome this by doing what you would expect, which is a pretty obvious thing. We're just going to replace our value of P with P hat to get our final result. So our confidence interval is going to look like our point estimate P hat plus or minus our confidence multiplier times the standard deviation, where we use the sample proportion p hat instead of the unknown population proportion p. So that's going to give us what we need. It looks very much like we saw earlier in the previous two videos when we're finding the confidence interval for population means. So let's take a look at a golfing example. Let's suppose you own a golf course and you're trying to attract more women customers, and so you conduct a survey to find out what proportion of women golfers are satisfied with their tee times. For those who may not be familiar with golf, the tee time is the time where you start your actual golfing. So those tee times are used to maintain a nice flow of golfers on the course, and typically tee times are about 7 to 15 minutes apart. So groups of golfers are 7 to 15 minutes apart. Okay, so you survey 85 random women golfers at your course, and 51 of them said they were satisfied with their tee time. Because you're trying to find the proportion of women who are satisfied, these 51 people here are called successes for your survey because they conform to what you are trying to measure, which is the proportion of satisfied customers. So these are what we would call successes. Our question then is, what is the 95% confidence interval for the population proportion P, which of course we don't know. That's why we're trying to infer about it. So again, here is our expression for the interval, the confidence interval for a population proportion. We have our point estimate plus or minus our margin of error, which is this entire thing over here after the plus or minus symbol. In this case, our sample proportion, the proportion of successes over the total number in the sample, is 51 out of 85, which is conveniently 0.6. Now, since we're looking at the 95% confidence interval, and we are assuming we're here on the normal curve, we're going to use the value of z star to be 2 as a real rough estimate, just like we did in a couple of videos before. Again, keep in mind that this is just a rough estimate. Better estimates can come from using 1.96 or from using text. Okay, so when I do all of my calculations for my confidence interval, I get here 0.6, which is my sample proportion, plus or minus all of this, which is my margin of error. This whole piece right here ends up being 0.1063. And so this is one way to write the confidence interval. The other way looks like this. So I would get 0.6 minus 0.1063, and that gives me my left side of my interval, 0.4937. And if I add 0.1063, I get 0.7063. So here is my 95% confidence interval. It's these two numbers here. And just as before, let's go ahead and interpret what this means. We are 95% confident that the interval 0.4937 to 0.7063 covers the true population proportion, which is fixed. So even though in this case we only have one sample, this is equivalent to saying, let's go ahead and take many, many samples of the same size, n equal 85, compute intervals for each one of those, just like we did right here, and 95% of those intervals will actually cover the population proportion. So we're pretty confident at a 95% level that this interval will actually cover the population proportion. It may not, but we're 95% confident that it does. Also notice that 0.1063 was our margin of error. That's about 11%. Think about this. Why do you think that that is so large? And a related question, what would you do in order to reduce that? You might want to think about that, and we'll get to that here in a minute. Recall that we got this result by using z equals 2 as our z star multiplier estimate. That's a good, in the ballpark, rough value that we can use. Of course, we know by now that 1.96 is better. And even better than that is going ahead and using technology. So let's just quickly review what that would look like if we were going to be using StatCrunch. So in StatCrunch, you would go to the Stat menu, and then below our Z and T stats, which we've just used in the previous two videos, you now see proportion statistics. Again, we have one sample here, and we have summary information. If we had a bunch of data inside of StatCrunch that we imported into StatCrunch, then we could indicate with data, give it the appropriate commands and settings, and it would give us what we want. But here, since we have a summary, we're going to use this option. The next screen would ask us how many observations do we have? So what's our sample size? So that was 85. And what is the number of successes? So as I said before, we define successes to be related to what we're measuring. Since we're measuring the proportion of women who were satisfied with their tea times, 51 of them did so, and so that is considered to be a success. We put in our confidence level of 0.95, which is what we were after, and then ask it to compute. And here is our confidence interval, which is very close to what we saw when we did this with a calculator or quote-unquote by hand. Again, they'll be slightly different because StatCrunch is using a much more accurate value for our Z-star multiplier. So let's take a look at the same scenario, but now instead, suppose we could sample 1,000 women instead of 85, and then we wanted to compute the 95% confidence interval in that case. Now, of course, there's a trade-off here. If this is a small golf course, you may not have access to 1,000 golfers. Probably very unlikely that you'll have access to that in most golf courses. The other issue is that sampling 1,000 people might be a lot more expensive than sampling just 85. It may take a whole lot more time. So there's trade-offs here as you consider what your sample size is going to be, and so those are things to pay attention to. However, if we think about it, the sample size is going to dramatically affect what our confidence interval is. If you think about the expression for the confidence interval in this case, because the sample size n is down in the denominator of the standard deviation, as n gets larger, that means the denominator of the fraction is going to get larger, which means the whole fraction gets smaller. As that gets smaller, that is going to narrow your interval. So if we went ahead and used StatCrunch in that case, and now we have, let's say, 600 out of 1,000 women indicate that they're satisfied with their tea time. So we're still looking at the same sample proportion of 0.6. Then you can see that our confidence interval goes from about 0.57 to about 0.63. So it's a much narrower confidence interval, but the price you pay for it is having to get a much larger sample size. In this particular case, if we looked at this interval and we computed the margin of error, recall from a previous video, we said that the margin of error was simply half of the distance between these 2 points right here. So if I took the total distance and computed that in this first part of this expression here, and then divided it by 2 to get half of that, then my margin of error is about 0.03 or 3%. So what we have then basically is an interval that's 0.6 plus or minus 3%. Sometimes in polling, you see plus or minus 3% reported on, especially around the times of elections. So this is a very common margin of error that's reported, and notice that you need a sample size of approximately 1,000 in order to get that. In this case, we noticed that the sample size reduced the margin of error from 11% before to about 3% now. A sample size of about 1,000 will do this, but keep in mind it depends on the Z-star value, our confidence interval level. In this case it was 95, but if we change that, that would also impact this. It's also going to depend on the sample proportion itself. In this case it was 0.6, so if that changed slightly, then you could expect the sample size to change as well. And that's simply true because the expression for the confidence interval takes into account the sample proportion value, the sample size, and the z-star value that comes from picking what your confidence interval is going to be. We see that once again in this expression. All of those things are going to impact what this looks like, so each one has a role to play. So just like before, we still need to ask, when is it safe to use these methods? Just like we had with the population means, and when we're computing confidence intervals for population means, the sample that we take for a proportion still needs to be random. Also, because we're assuming that we're using z-star values, we are then assuming that our sampling distribution for sample proportions is normal. And the only way that happens, as we saw in a previous topic, is if n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. In a previous topic, we saw that these two conditions, if these were both true, then we could assume that the sampling distribution of sample proportions was normally distributed. That then allows us to use all the calculations and the StatCrunch calculator to do the computations that we need in order to compute the confidence interval. Okay, so that's basically the end of this video. We now know how to do inference on population parameters, whether they're means or proportions. We had three cases. In the case of a mean, we use the normal distribution when the population standard deviation is known. In the case of a mean, we use the t-distribution when the population standard deviation is not known. And in the case of population proportions, we're going to revert back to our previous knowledge about standard deviations for those sample distributions and adjust accordingly that we just saw in this video. So that ends this video. In the next video in this topic, we'll look a little bit about how to compute sample sizes in various scenarios, and we'll do a quick little exploration into what we mean by 95% confidence interval. So that does it for today. I hope the video was useful.